So welcome back, and once again we're looking at practicing and trying to understand and figure out what it means to work with samples from a population versus individuals from a population. The thing that we're looking at in Module 9 is what changes about the distribution of the values when we are looking at a sampling distribution versus the original population upon which the distribution of all possible samples is based. So it kind of helps us to once again revisit the idea of the central limit theorem. And in the video that I give where we talk about this, you see how the underlying distribution of the original population changes as we begin to look at the distribution of samples in relation to it. What we saw with the central limit theorem has some very basic ideas. In working with populations, we know that the mean and the standard deviation of the population are problems that we are working on need to be divided into two types of problems. There's going to be two types of problems that you'll look at. One is situations where we're selecting one member from the original distribution, and then other situations where we're selecting a sample, where a sample could be anything greater than one from a population. As we saw from the readings of the section, when it comes to a population mean, and this is true also with proportions, though we're not going to spend as much time on that beyond your reading assignment there, at least at this point. When we take a sample from a population, the central limit theorem says three things basically. Number one, when n is greater than 30, or an n of any size, if our original population is distributed normally. So there's two requirements. Either A, we need to know that the population from whence our sample is coming has a normal distribution. And then two, it doesn't really matter how our original data was distributed if we have an n that's greater than or equal to 30. If either of those two things are the case, either we're taking a sample that's larger than 30, or we know that the underlying population that we're drawing from has a normal distribution, the distribution of all possible samples, which is the distribution of our x bars of size n, are approximately normally distributed. Second, the center or the mean of our distribution of samples of x bar, which we also call sometimes the sampling distribution because it's a lot easier to say than the distributions of all samples x bar of size n, is the same mean or center of the underlying variable or population x. Third, the standard deviation. This is where we really see some changes here. The standard deviation of the distribution of samples of size n, which is again called our sampling distribution, is smaller than the original distribution x bar. Specifically, what we see in the distribution of our samples, or the sampling distribution, is that the standard deviation of that distribution is equal to my original standard deviation of my x. X is just our original data, so I like to put that there, divided by the square root of our sample size n. So what does that do to us when we are looking at specific problems? Well, let's take a look at a couple of examples, and I'm going to basically just run through one. And what I want you to do is to look at how I'm drawing and using my picture here for these. And we're going to apply the sample, or the stuff that we've derived here. Number one, that our standard deviation changes. The second, we could actually visualize as being the mean of the sampling distribution being equal to the center of my original data, or the mean of the original data. So mu sub x bar, the middle or the mean of my samples of size n, will be equal to the mean of my original data. So the sample, the centeredness of my distribution remains the same, but the spread changes quite a bit, and the spread is what we see with our standard deviation. So we're going to look at a scenario, and I'm going to take you through two different things, and then this of course applies when we're working backwards using invert norm. The same thing. The main thing we need to look at is our what our standard deviation is. So we're going to take a look at two scenarios, and our example begins with talking about the annual salary of teachers. So the annual salary of teachers in a certain state X has a mean of 54,000 and a standard deviation of 5,000. What is the probability? And we're first going to look at on this slide that the annual salary of a randomly selected teacher from the state is less than 53,000. And then second, that the mean annual salary of a sample of 100 randomly selected teachers from this state is less than 53,000. So same value, 53,000, is kind of the one that's under question, and the area to its left less than that in both cases. So we're going to start off with looking at the distribution of X, which, as we see over here, X is our just teacher salaries. And we're told in our original problem that the teacher salaries center around 54,000, so that's the average. But then they deviate from that by about 5,000. Okay, so here's my center of the underlying value X, which is teacher salary, and then the standard deviation is 5. So at the center, of course, we want to put our mean. So we have mu here. And of course, that means this is the center of the Z. And then we go one standard deviation to the right. So 1 to the right, 2 to the right, 3 to the right. And as I do that, we're looking at the corresponding Z values for these. 59 is 1 standard deviation to the right, so that is a Z score of 1. And if we subtract 5, we get 49. That's -1 standard deviations. And then this is -2 standard deviations, subtracting 5 again, and then -3 standard deviations. I want you to make that connection between the X and the underlying deviations from that, which is our Z. Z is always telling us the number of deviations our data values are from the center. So our value of 53, and of course I put these into thousands, so this is money, in thousands. Try to squeeze that in there. 53,000 is just barely to the left of our center, right? It's at 53. And if we took a look at the Z equivalent of that by using our Z formula, we could go 53 minus 54 divided by this 5, which is my standard deviation. So that's -1 over 5, so -0.2, which you can see in relation to 0, 53 tracks to about -0.2 as far as its Z-score. So it's -0.2 standard deviations to the left. Now with our technology, it's not necessarily important to know that, because we don't have to know what the Z-score is, but I do want to do that just so you can see the connection there. And we want to know the probability of selecting someone that's less than that, so I'm going to go ahead and shade here to the left. Now I know many of you have used the Z-score in finding your area, but with our technology we don't have to do that. If I want to know this area here, which is going to be my probability, so my probability setup, and I'm just going to give myself some room here by erasing a little bit of this. I'm going to write this over here. What we're looking for is that the probability that a randomly selected teacher X would have a salary that's greater than 53,000. Again, if we're using 53, it's okay to do that, just remembering that these are in thousands, right? So whenever we're talking about the results we get along the x-axis, we want to interpret those in terms of thousands. All right, so to find that area, we're going to use normal CDF because that's what we do. And we can see that we have a unbounded left-hand area that we're after. So we're going to put something really big like negative 1,000. Of course, negative 1,000 doesn't mean much in terms of, actual salaries. Nobody would get paid negative 1,000 to teach, obviously. But the idea is just to get an infinite thing that's very different than your lowest value that you have written there. So we're going to put negative 1,000 all the way up to 53 is my upper boundary. The mean of this data set in terms of teacher salaries is 54. So notice that instead of comma 0, comma 1, we're putting 54 and then, and then 5, which is my standard deviation. And what we get from that, I'm going to plug into my calculator. You can do the same. Is 0.4207, which is kind of what we expected. Again, use the logic here as you're looking at your picture and the answer you're getting. It means you want to standardize this and practice this a little bit. But the area that we found here, which we know is a little less than 50%, is 0.4207. So about 42% probability that we would randomly select one teacher that has a salary of $53,000 or less. Okay, so how does that change as we approach B here? Let's go to our next slide. Now what we note that my spread went from all the way to, from negative 39 at negative 3 standard deviations all the way up to 69 at positive 3 standard 1. We put X because we're talking about the original data, not a sample that we've taken a mean from. So we just have X here, and using the correct probability notation, we tie the area that we found with normal C. It has a very different distribution as we see here. It was much easier for us, or more probable for us, to select a single teacher that made less than 53,000 than it picture is the distribution not of individual teacher salaries, but rather of X bars. This is a picture of my X bars. Specifically, it's a picture of if I were to go out and take samples of size 64 and record the mean, so I take those, I'm sorry, this N is supposed to be 100, not 64. I changed that. Because it actually gave me easier results to write along my x-axis. That's why I changed it. So we take a group of 64, we take their average, we plot where it ends up. And let's say we continue doing that an infinite number of times. What we find is we get a own unique distribution of these X bars. And so this picture that we're trying to draw out here is that distribution. It's the distribution of an infinite collection of samples of size 100 selected randomly from my population that I take those 100 and I take their average. And then I organize those infinite number or thousands and thousands of samples of size 100. What we see, according to the central limit theorem, is that the center of, or the mean of all of those samples, so if I were to take every sample that I've taken of size 100 and I averaged those averages, averaged those X bars at, they would center themselves around 54, just like my original individual teachers did. Again, that's the mean of the teachers will be equal to the mean of their samples of size 100. But then we also saw, and so over here we have that, the the center of my curve is still at 54,000. But the one thing that's changed is that the deviation or the spread of these samples becomes smaller and smaller as my samples become bigger. Specifically, if I look at the individual deviation of the individual teachers, if I divide that by the square root of my sample size, that actually gives me the deviation of this new distribution. So no longer am I adding 5,000 every time I move to the right. I'm adding 0.5,000 or 500 as I move to the right. And so we have a very different spread of the data. If we go back and look at the previous spread, well, these don't do that. The samples of size 100 only spread out from 52.5 to 55.5. So now when I look at the probability, and again I'm going to write this out, the probability that I would take a sample. So notice that as I write to differentiate between these two, instead of just putting x, I want to put x bar, and maybe even I can put 100 here to show what the sample of that mean, what the sample size was for that mean, is less than 53 is equal to blank. I need to look at my new distribution. Notice 53 is not right next to 54 anymore. It's in fact 2 standard deviations to the left. And using the empirical rule, that tells me that my area, because remember the empirical rule is not exactly exact, it's kind of an approximation. This is the area now that I'm looking to find, right? So I'm going to label it. And I'm going to find this. Now, if we want to look at how, in relation to z's, this would be 0, 1, 2, 3, -1, -2, -3. We can also find that z value here. The z for this distribution is, again, 53 minus 54. So it was before. So my data value under consideration, x, minus the x bar, or the mean of the, not the x bar, sorry, but the mu sub x bar, divided by the standard deviation. But the standard deviation is 5 over the square root of 100 now. It's not what it was originally. It's not 5. So the z value changed as well. And if you want to enter this into your calculator, you want to put parentheses along this top operation because it's a subtraction. That's kind of the lowest of the order of operations, so we want to bump this up. And also we want to do this division before it's divided into the division that we have here. So we also have to put this into parentheses. But this comes out to be 1 over 0.5. And 1 divided by 0.5, or 1 divided by a half, is 2. And we see that -2, sorry. And that's -1 on top. And so that's where we can see the z value, the standard deviation, is -2. So at any rate, again, you don't have to do this, but there are times where you want to know, well, what is the standard score for this data set? Where exactly should this fall on my x-axis? So we know that -2 is a relatively extreme position on the left. Well, to find the area, again, we're going to use normal CDF, but we have to put the correct things for this particular distribution. We're going from something extreme, like -1000, all the way up to 53. And the mean is still 54, but the standard deviation is now changed. The standard deviation is, and I'm just going to put it works out really nice in this one. As far as the standard deviation, it comes out to be 0.5, but a lot of times it gives you a decimal. So rather than try to input a decimal out to a number of places, I'm just going to put 5 over the square root of 100 into my calculator. And that means I'm not having to round at all. In fact, now that I did the previous one, if you go second entry on your calculator, it actually pulls up your previous entry that you spent so much time and care typing out. And I could just use my arrows to go back and change the one thing that's changed here, which is my standard deviation. 5 divided by the square root, so second x squared is where your square root is located, of 100, which of course we know is 10, so you could actually just put 10 in there. And we get 0.0228. And so that's the area. I'm going to label that up here. All right, every time we use normal CDF, we're finding an area. So we want to label it up here, and this is something I'll be looking for at your test, that you're labeling your curve. So if you've shaded an area, you need to tell me what is the area of that. And you need to mark along here where your value is that is under consideration. Here it just happened to fall on a whole number deviation. And then, of course, to express it correctly in probability notation, 0.0228. Notice that I differentiated in this one, in my notation, from a sample by putting x bar here rather than just x. On the probability notation, which we have written, here. So we see a connection not only between my probability notation, but that's reflected also on the graph. So on my graph, I've got my area shaded and labeled with the area, and it matches with the probability notation. And we're dealing with a distribution of means, and so I've changed the standard deviation along the x-axis compared to what it was with the original data. So those few things are what you want to really pay attention to as you're labeling your graph. We're putting not only, and on this I've taken it out to, oops, sorry, I meant to highlight that, not cross it out. Let's see if I can erase that. Along my x-axis here, I've written it out to 3 standard deviations. You only need to necessarily take it to 2. Most of the time is what I'm going to require of you. And your answer should make sense. I've got a very small area here that we've drawn and filled in, and it matches with the area that we've labeled to it. I know that I'm expecting a very small area because it's in a tail region. We know the tails have a very small percentage. And that's logically reflected in my picture and in my probability. At any rate, practice these things. If something is not making sense, don't just move on and go, oh, well, I don't get it. Try to figure out why. Are you labeling the x-axis correctly? Are you shading in the correct direction as described in the problem? Am I talking about a population that I'm sampling from? So I'm taking samples from a population, or am I talking about taking an individual from the individual population? Because that individual population, for us to select 100 teachers and to have their average come out less than 53,000. And that's the idea of sampling. When we sample, we get values that are closer to the center, closer to the mean, and therefore it changes the layout of my probabilities. I wish you luck as we proceed through this week, and I hope this was helpful to you as well.